Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion, so I'm going to briefly review it before we dive in. So consider that we have a particle that's undergoing circular motion, and we have that its acceleration can be decomposed into two components. One of them is a centripetal component that points to the center of rotation, and the other one is a tangential component. Okay, so the centripetal component, centripetal acceleration, is equal to v squared divided by r, where v is the speed of the object and r is the radius of the trajectory. And this centripetal component accounts for the change in the direction of the velocity. Okay, and the centripetal component exists even if the speed is constant. The tangential acceleration, on the other hand, accounts for the change in speed and is equal to the derivative of the speed with respect to time. Okay, so now we can go on to the exercise. So we have a car that's traveling through a road represented in blue in the figure, and we want to know what is the maximum speed that a car can have, given that the radius of curvature at point A is r, such that the car passes through point A and still maintains contact with the road. Given this information, we have to assume that the car maintains the same speed, the same constant speed, and then passes through B, and we have to calculate what is the normal force that the road exerts on the car at point B. So let's first find the velocity, the speed that the car must have at point A. So consider that this here represents the car, this block here. The forces that act on the car are the gravitational force that acts downwards, and we also have the normal force that the road exerts on the car. These are the forces that act in the vertical direction. Notice that since the car is moving in a circular path, then there is a centripetal acceleration pointing downwards. Okay, so we have that mg minus the normal force is equal to m times the centripetal acceleration, which is v squared over r. Now, in order for the car to maintain contact with the road, n must be at least 0, so it must be greater or equal to 0. So in the worst scenario, when the car is almost losing contact with the road, n is equal to 0. Okay, and when n is minimum, v is maximum. That's what we want to calculate. So we're left with g is equal to v squared over r. So v must be equal to the square root of gr. This is the maximum speed that the car can have. Okay. Now the car maintains this same speed and passes through point B. At point B, we again can draw the force diagram. So we have the gravitational force acting downwards and the normal force acting upwards as ever, but the centripetal acceleration now is upwards because the circle changes. Okay, before we had that the center of rotation was below point A, but now the center of rotation is above point B. So the centripetal acceleration must be pointing up now. So we have that n minus mg is equal to m times v squared over 2. Okay, and the normal force will be mg plus mv squared over r. Now, v squared is gr, according to this formula here. So we have mg plus m gr divided by r. This is equal to 2mg. So the normal force that acts on the car is 2 times mg, which concludes our exercise.